the topic of our research, and actually my presentation is about bidirectional Thion liquid damper, or BTLD, for stabilizing offshore wind turbine substructures. I can say the floating offshore wind turbine is the primary solution for expanding wind power generation into deep waters in the future. So effective FOWT operation includes platform stability, power regulation, and load reduction. And so developing simple low cost and low power actuation schemes for floating offshore wind turbine platform stabilization is highly desirable. So at the first step, I explain more about the FOWT stabilizers. As you know, there are different stabilizers, different kinds of stabilizers, including mooring line and additional control actuations, including TLD, TLCD, and TMD, and so on. So the main objective of the current research is the utilization of a BTLD. BTLD is by acronym of bidirectional Thion liquid damper as a passive control device integrated into the body of a barge-type floating offshore wind substructures. Actually, we modeled a special kind of FOWT, barge-type floating offshore substructures. So this approach aims to control the pitch motion of the substructure. Actually, the final goal is the mitigation of the pitch motion of the substructure. Through the selection of optimal geometry and positioning, we try to find the optimum geometry of different Thion liquid damper devices. I will explain. As you can see in this figure on the top left and right, two kinds of Thion liquid dampers, bidirectional Thion liquid damper, or BTLD, on the left, and the BTLCD, or bidirectional Thion liquid dampers, column dampers, on the top right. And on the down left and right, you can see the integrated model, integration of a FOWT substructure and BTLD and BTLCD. We try to find the optimum geometry of the devices, and also optimum water filling level, and also the optimum position of the BTLD. So, however, this topic is very new topic, and so you cannot find a lot of papers in this topic. I think there are only some papers in this about this topic and this field. For example, the first paper is from Park and his colleagues in 2020. In this paper, they used TLCD within the nozzle of a TLP, floating offshore wind turbine, and you can see in this figure. Sorry. And the simulation results, their simulation demonstrate the effectiveness of the orthogonal TLCD, reducing extreme loading. And in another paper by Zhou, I think it's all 2023, they modeled TLCD in a semi-submersible, and they confirmed that a TLMCD can be a better alternative to traditional TLCD for a floating offshore wind turbine. And finally, in this paper from Han et al., they investigated the vibration suppression of a barge-type floating offshore wind turbine using a TLCD. However, this floating offshore substructures is a bit different with the floating FOW substructure we use, because in our research we consider a moon pool at the middle of the bar. It's a bit different with this paper. Okay, we modeled some codes by using OpenFOAM, and in this figure you can see we also developed and modeled octagonal floating offshore substructure. You can see here in this figure. Okay, as I said, we use OpenFOAM and we develop some codes in OpenFOAM. So we consider the float as viscous, so Navier-Stokes equations were employed as the governing equations. Here you can see a schematic sketch of the integration of the substructure floating offshore and BTLD. Here is a BTLD around the moon pool, and the gray one is the substructure. Okay, after development of the code, we validated the model. Here is only one test case. Here I only present one of the test cases. And after the model validation, first we developed a code to model only the floating offshore wind turbine substructure for this case. Here is, you can see specification and some parameters of the floating offshore wind turbine substructure. And the pitch motion of the structure for different mesh size, because you know the first step and the most important issue is the mesh size independency. So we modeled for different mesh sizes. Here, medium, fine, and very fine. And after the mesh size independency, we modeled for different wave periods. As you can see in this figure, for example, here is 10, 12, 14, and 20 seconds. These are the wave periods. And the first figure is heave, and the second one is the pitch motion of the substructure, as I said, for different wave periods. Okay, based on the results, we actually summarize and extract the RAO of the substructure, heave RAO and pitch RAO, and compare with the results of Chuang et al. Experimental and numerical, and actually we validated the model again by using these results. Okay, as I said, we tried to find the optimal geometry of the BTLD, or bidirectional anti-rotating damper. As you know, we could model a huge number of BTLCD. So first we modeled a huge number, and we selected some cases. As you can see here, we summarized 9 cases. We selected 9 cases, and also for different baffle height, because you know in a BTLCD we have 4 baffle, so that actually the baffles create a phase lag, make a phase lag between the fluid motion inside the tank and the wave motion, so it can decrease the pitch motion. So the critical issue and the main subject in BTLD is the phase lag. We have to find the optimum baffle height to find the optimum case. We modeled 4 baffle heights. So as you can see, we have 9 geometries and 4 baffle heights. Actually, we have 36 cases for 9 geometry and 4 baffle heights. After modeling 36 cases, here is some results for the pitch motion for 4 cases as a sample, and for 2 meter baffle high, you can see here. And finally, we summarized all results for 36 cases in these figures. On the top left, you can see the maximum heave. For all cases, the horizontal axis is the baffle height, 1, 2, 3, 4, 5, 1, 2, 3, 4, and also the 0. And also the vertical axis is the maximum heave and pitch for all cases. Based on the results, you can see the optimum case is the case 9, the red line here and here. And for baffle height, for 4 meter baffle height is the optimum case, this point. As I said, we had to optimize the geometry first. Second one is finding the optimum water depth inside the tank, and finally the optimum position of the tank. Here you can see a sensitive analysis of the filling water level. Actually, we filled the tank with different water level. The horizontal axis is the HW or water high inside the tank, and here the vertical axis is the pitch and heave. Finally, we found that 6.7 run is the optimum water depth. And also we did a sensitive analysis for the BTLD location inside the substructure. Actually, distance between the bottom of the substructure and bottom of the TLCD. We consider this parameter as D, and we found the optimum D at this point. It's around 2.5 is the optimum position or location of the BTLC. Actually, we optimized sequentially. We follow and we use a sequential procedure for to find the optimum case. First, we optimize the geometry, filling, water filling level, and finally position of the or location of the BTLCD or BTLD. Sorry. Okay, after finding the optimum geometry and BTLD, here you can see we modeled the suggested case for different wave amplitudes in these figures. The x-axis is the wave amplitude and the vertical axis is heave and pitch. You can see here I have to explain FOWT is the original floating offshore. The second one is the integrated system, FOWT and BTLD. For the pitch, you can see the red line, pitch motion is always less than the pitch motion of the original FOWT. However, for the heave, the suggested system cannot mitigate or reduce the heave motion, but for the pitch motion, always pitch motion is less. I have to explain this model is only for the natural period of the substructure. This model for the natural period of the substructure. And here you can see we model for different wave periods. So, for example, this figure, we compare pitch motion of the substructure for different wave periods. The x-axis is the wave period, and vertical is the pitch. As you can see, around the natural period, pitch is for the coupled or integrated system is much less. I think it's around 30% less. However, for the wave periods, more than, I think, around 16 seconds, the suggested system not only decrease the pitch motion, it's increased the pitch motion for very long wave periods, more than 16 seconds. You can see from this point, the pitch motion is more. And also for the heel, unfortunately, the suggested system cannot mitigate. However, our final goal was the pitch motion. After optimization at BTLD, we focus on the BTLCD, as we followed the similar procedure to find the optimum BTLCD. And first, I selected 10 cases. For this case, we don't have, there's not baffle, we have an orifice actually. At the middle of this part, you can see an orifice. We try to optimum the opening percentage actually, instead of baffle high. So first we modeled 10 cases with different opening percentage. And here you can see OP is the opening percentage, 30%, 60%, and 90%. Based on the results, you can see in this figure, we found the optimum case. And also we did a sensitive analysis for opening percentage in this figure. So the results show that case 6 with a 60% opening percentage is the optimum case. And after finding the optimum BTLCD, we focus on a new substructure geometry, octagonal, and we define different geometry in this figure summarized for different A. And we model these cases. So after modeling, here we summarize the results for different A, and here is the pitch, maximum pitch, and E. And we found out the octagonal platform with a corner length 6 meters A and E. About 10% of the platform length is the optimal platform. Actually, we found the optimum octagonal platform or substructure based on the pitch motion of the platform. Okay, so at the first step, we found the optimum BTLD. The next step, optimum BTLCD. Finally, optimum octagonal. We integrated the different cases together. Here you can see in the final figure. Here is only bars. The original FOWT is the first one. Integrated of bars BTLD, bars BTLCD, octagonal without BTLD or BTLCD, octagonal BTLD, and octagonal BTLCD. Here we have 6 cases. Original BTLD bars, original octagonal, integration of bars and octagonal with BTLD and BTLCD. And here is the maximum heave for different wave periods. And here also the similar, but for the maximum pitch and wave periods, bars, BTLD, BTLCD, octagonal, BTLD, and BTLCD. We can interpret and discuss a lot about this figure. For example, I summarize only some results. BTLCD integrate with a barge substructure performed better than BTLD. However, it's only for wave within the natural period. But in general, BTLD is better, but for the wave period around, very close to natural period, BTLCD is better. And also, comparison of the bars and octagonal show that the octagonal is, motion of octagonal is less than the bar substructure for wave periods, less than 13. However, as I said, in this figure, we can discuss more and more, but I only summarized 2 main results obtained from this result and figure. Okay, thank you so much.